So today we'll discuss first. We have already completed operating results in the last two classes. Okay. So module 3, there are two parts. The first was operating results. Okay. So this we completed in lesson 15 and 16. Okay. Now next two classes we will discuss composite generation and transmission systems. So in this class we will see how numerically we can obtain the reliability of composite generation and transmission systems. And next class we will see some advanced concepts. Lesson 18 we will see some advanced concepts. Okay. See, the point is that transmission system is very reliable. We don't have much problem with transmission output. It is the distribution system that is the problem and the generation, but not transmission systems. Okay, so it is a very small part of the syllabus. Transmission system. One of the basic elements in power system planning is to determine the generating capacity required to satisfy the load requirements. So this was the topic of almost the whole of module 1, which is the most important topic, generation capacity reliability evaluation. This is whether, so what was the objective? Whether there is sufficient capacity in the system to generate the required energy to meet the system load. And we computed two indices, loss of load expectations and loss of energy expectations. So these are the most important indices for power system reliability evaluation. The second one, equally important, is suitable transmission network. Okay, so you need a suitable transmission network. Okay, the transmission network can be divided into two parts. One is the bulk transmission and distribution. Okay, so here this happens at very extra high voltage. Okay, happens at extra high voltage. The distinction between these two areas is not only on voltage basis but also includes the function of the facility within the system. So distribution will be part of module 4. Okay. In module 4 we will see distribution. So this module, a small part, we are focusing on transmission. Bulk transmission facilities must be carefully matched with the generation to permit energy movement from the sources to points at which subtransmission distribution can provide direct radial power. You must be knowing that most of the distribution systems are radial distribution systems, not based. Okay, because there are advantages of radial distribution system. Distribution system design is almost entirely decoupled from the transmission system development process. So the parameters that we are going to use for distribution system do not apply to transmission system because it is structurally different from the distribution system. Conflict between these two systems can be accommodated by using load point indices. Okay. So mostly you write down relation is what? Load point indices. So this is what distinguishes transmission system from generation system. So we compute load point indices. For transmission facilities to maintain adequate voltage level. So these happen at very high voltage, known as extra high voltage or ultra high voltage. Okay. And we are concerned with thermal limits and stability limits. Okay. Thermal limit is related to I square R loss of the system, whereas stability limit depends on the generation power equation. Okay. That is the stability limit. Adequacy evaluation is concerned with satisfying the load demand, which is mostly related to generation systems. Adequacy evaluation. Whereas transmission system reliability is more with respect to security evaluation. Okay. Write down these two terms: adequacy evaluation and security evaluation. So these two terms can be asked as a 2-mark question. What is the difference between adequacy evaluation and security evaluation? Okay, where is that? The analysis at load point L. So here, as I told, it is load point indices. So we are concerned about a load point L in this case. Can be done using LOLE, LOE of impedance generation techniques. The configuration can be radial or network. So today we will discuss only in lesson 17 we will discuss only the radial part, and in 18 we will just have a look of network, including dispersed generation and load part. This is mostly applicable to distributed generation systems, modern distributed generation systems like integrating wind, solar and different parts of the network. The problem of assessing the adequacy of generation and bulk transmission is to provide a dependable and suitable supply at the terminal stations known as composite system reliability. So in this case we are not evaluating transmission system as isolated system, whereas that will be applicable to distribution systems. But here we are combining generation and transmission. Okay. So whenever we talk about transmission system reliability, we actually mean the combination of generation and transmission system, not only the transmission system, because transmission system reliability as such has no meaning because it is not connected to any load point. Okay. And it is taking power from the generation. Okay. Draw this network. So this is a typical radial configuration. Draw this. Okay. So we have a generator. So this is a typical network that we are going to see today's class. So we have a generator, transformer and a double circuit line. Okay. The analysis of load point. So this is the load point. This load point can be a transmission substation or a distribution substation. Okay. The analysis at the load point here can be done using these approaches. The linking configuration between the generation source and the load point may not be a simple series parallel type, but can be complicated as an HPDC. So when you say HPDC evaluation, reliability evaluation of HPDC systems, then it will be complicated because of the involvement converters. Okay. Where transmission capability is dependent upon the availability of rectifier and inverter bridges. So it becomes complicated. It is not part of the syllabus. So for this transmission system reliability approach, we use conditional probability. Here, so till now we have been using only the binary distribution, but here we are going to use the conditional probability approach, which was covered in the very first or second class. Many probability applications in reliability evaluation assume that component failures within fixed environments are independent events. Okay. We assume that the component failures are independent events. Okay. This may or may not be true. It is however entirely possible that the component failure can result in system failure in a conditional case. For example, what is the probability that the system fails provided this component fails? Or what is the probability that load will not be met provided one circuit is disconnected, one transmission line is disconnected? This can occur in parallel facilities that are not completely redundant. If the load can be considered as a random variable and described by a probability distribution, mostly normal distribution, okay, then failure at any terminal station due to component failure is conditional upon the load exceeding the defined carrying capability. Okay, load point failure in this case may be defined as inadequate voltage or available energy. Write down this. Load point failure can be considered. Load point failure can be considered as inadequate voltage or available energy at the customer point. Inadequate voltage or available energy at the customer point or customer bus. Write it up. And finally, what exactly conditional probability means? This boils down to this equation. Okay. What is the probability that event A will happen provided event B has happened, or a number of events B1, B2 up to Bn has happened? So If the occurrence of an event A is dependent upon a number of events Bi, B1, B2, B3 or Bn which are mutually exclusive. So in that case, not independent, mutually exclusive but not independent. So in that case, we have to use this formula. Okay, so it's like what is the probability of load not met provided line 1 fails and line 3 fails. Okay, so you have to use this formula. Write out the formula for the conditional probability. Right. Okay. Yes. So write down this formula. The probability of value in K at bus K in a network is given by this formula. Okay, just write down this formula. How it is going to be used, we can see in the problem. Where Bj, an outage condition in the transmission, don't need to write this one, just write the formula. The Bj is an outage condition in a transmission network. Pbj, probability of the genetic capacity outage exceeding the result. P1j, probability of load at bus K exceeding the maximum load that can be supplied. Okay. Then this is the frequency approach. So you can have a probabilistic approach or you can have this frequency and duration approach. Okay, it is this formula where Fpj is the frequency of occurrence of outage Bj. Just write down these two formulas. Okay. So these are the equations that can be derived from the earlier part. Now this is the question. So if it comes in the exam, it will be an 8 mark question. Consider a system having 6 into. Just write down the salient points of this question. Okay, so this is a system. See what we are discussing. We are discussing composite generation and transmission system. Both information should be there in the question. The first is 6 into 40 megawatt unit. What is the capacity of the system?
6 into 40 and then
240 megawatt. That is the capacity of the system. Now, unavailability is 0.02 is actually F1, post operator. Unavailability means F1. And what is lambda?
Failure rate.
Failure rate. 0.01 failure rate, which can be 3.65 failure per hour. How? Multiply 355. Similarly, what is new? Repair. So it is 0.49 repairs per day, which must be equal to 0.49 into 365. How much? How much is this? 0.49 into 365. How much? 0.49 into 365.
178.857.
178.85. So this is that much entire by 8. So this is wrongly written 85. Transmission elements, 2 lines. So transmission system, 2 lines, double submitted. With same lambda is different. You see it is 0.0, it is 0.5 value per year, and R is 7.5 hours per repair. That is how it is given, and this is the FOR. So just look at the FOR of generating system and transmission system. For transmission system, very less post operating rate. Generally not used for maintenance. Peak load is 180 megawatt. Mention all the select points mentioned. Peak load is 180 megawatt. So load is represented by a straight line. Low duration curve, 100 to 74%. So this is the load duration curve. Okay. 100 to 70%. So this is 100%. This is 70%. And how much? This should be 180 megawatt. And what is this? 70%. 180 to 70%. 180 to 47 is how much?
180 is 70%.
126. So that this is 126 megawatts. So this is the duration curve. Obtain the generating capacity model and capacity of the system. Obtain the transmission capacity model. So this is what we will discuss as numericals. Beyond that, you have to consider the flow duration curve, find out the reliability. We are not going into that. We will just see how the generation model is obtained. After that, everything is same as model 1. Okay. For the above system, obtain the composite state probabilities and frequencies. Okay, assuming individual line carrying capacity to 160 megawatt. Compute the load point indices. Okay, so many questions are there, but this we can think of as assignments. But from exam point of view, only we are concerned about this part. Obtain the generating and transmission capacity model. So because beyond that it will be very cumbersome and time taking, so we will focus only up to developing the model, generation model. Because beyond that the steps are exactly similar to what we did for generation system. Okay, and we are not going to repeat it. We will just see how the composite model is. Okay, and that is for your focus.
So what's it?
Okay, so we'll go to the exercise C, see the solution. Okay, so this is our system. 6 generators, 40 megawatt total capacity, 240. Okay, FOR is 0.02 failure and repair rate, which is multiplied by 365, as you see. This will be multiplied by 365. This into 365. Peak load. Oh, I have made a mistake. So I have multiplied 365 here. No, it's okay. This 365 values per year. This is 178 values per year. And this is the peak load. You told me 126, right? So this is 126. Okay. This is for the load duration curve. But as I say, we won't go further. This is exactly similar to as we did for generation system. We have used load duration curve in the form. Okay. The main difference with respect to generation system reliability evaluation is this transmission line. Okay. So here there are two lines having total capacity of 320 megawatt. Our generation capacity is 240. Transmission is 320. So we are safe. We have a much higher transmission system capacity, and the outage is very less compared to generation. Generation may be out, but transmission will be out. Okay. So how to develop this model? Generation capacity model. This equal to. Okay. You can develop the generation capacity model, right? Chemical generation capacity model. We have to use FOR. So how many units are there? 6 units. So you can have 0 outage, 1 outage, 2 outage, 3 outage, up to 6 outage. Okay. Similarly, when the generation are outage, then capacity outage is depending on the capacity. 1 outage is 40 megawatt hour, 2 outage is 40 into 80. 3 is 40 into 3, 120. 4 is 40 into 4, 160. 5 into 40 into 5, 200 megawatt, and so on. Then available capacity is total capacity minus outage, right? And this exactly they are using the same formula. What is the formula? That we are going to use. Total generated is 660. Okay. What is the failure rate? What is the failure rate?
0.02. 0.01. U 02. 0.02.
To the power 0. Right? No generator is out. Into 0.98. Right? That is availability 1 minus 0.02 to the power 6 minus 6. Right? That means 6. So find out, is it same as this? Just find out. So this is essentially 0.98 to the power 6. Is it this? Just check. 0.98 to the power 6.
So 0.8885 units.
Yes. Now see. Okay. So accordingly you can calculate the probability of failure. But here departure rate. Okay. What is departure rate? In simple two-state model, the departure is from operating to fail with a failure rate or fail to operating with repair rate. Okay. So what is the failure rate?
0.01.
0.01 occurrence per year. What was the occurrence per year?
3.65.
3.65.
Failure 3.65 and repair plus 178.85.
178.
Okay. So in this case, there is no failure, isn't it? Zero capacity outage.
Failure the total.
Okay. So as you see here, there the formula is written, how it is calculated. So this is S6. What is S6? The failure rate. S6 is the failure rate into 6 minus 0, because no generator is out, all are operating. So all the generators can fail, right? So the departure rate is from operating to failure for all the 6 generators. So 6 into 6 minus 0, L6 mane how many generators are out, right? So 6 minus 0, okay, 6 minus 0 into 3.65, right? Plus repair into L6, 0. No generator is out, so there cannot be any departure for repair, isn't it? No generator is out, all are operating, all 6 are operating. So that means they can only fail, only can go in one direction. Okay. So if you do that, use that formula, you will get formula. Okay, if you use that formula, you get 21.9. Okay, clear? Again, for the second case, what will happen? Here, 5 generators are operating. One is already failing. So what is the departure? Departure can be 5 failures. 5 failures. That means 5 into compute 5 into 3.65.
18.25.
5 into 3.65 plus 1 generator has failed. It can be repaired. Plus 178.85. How much is this?
197.1.
Yes.
197.
Right. Similarly, in this case, you have 2 generators which have failed, whereas 4 generators are operating. So that means 4 failures can occur. 4 into 3.65 plus 2 repairs can occur, because 2 generators is already out. 2 into 178.85.
372.3.
372. Okay. So accordingly, it is already used in the Excel. The formula is used there, so you can calculate the departure rate. What is frequency? We have seen in the frequency and duration approach. So frequency into departure rate. Frequency into departure rate is equal to, sorry, probability into departure rate is equal to frequency. That we know. Multiply 1, check. 21.9 into 0.88 must be equal to 19.39. Okay. Similarly, 7.1 into 0.108 must be equal to 21.36. So this is the frequency. Okay. So in the exam, if you are asked for the generation system model, then if you complete this whole thing, you get 4 marks. Okay. This is 6 marks actually. If this whole question comes for the generation system, it will be 6 marks. For the transmission system, it will be 2 marks. So if you complete this part, then you get 6. Next. How to obtain a transmission system model? This is new to you. Okay. Now there are only 2 transmission lines. So how to develop the capacity outage table? Either no line is out, or one line is out, or both lines are out. Okay. Capacity outage depends on the capacity of the transmission line which I have taken as X. Because it is not given the capacity of each transmission line, it is actually 160. Total transmission capacity is given. How much is given? Transmission capacity 320 total capacity. So each transmission line is 160 megawatt. So X is actually 160 megawatt here, but we don't bother about that. We just write 0x. So capacity outage is 0. Capacity outage is 1 transmission line. Capacity outage is 2 transmission lines. Okay. So total capacity is 2, 1, or 2. Available. Depends on how much is out. Total minus how much is out. Now how to obtain this probability? Same formula. But in this case, you are going to use 2C0. What is the transmission failure? For
0.0.
0.000. U for transmission failure.
0.0004279.
4279. To the power 0, because no transmission is out for the first case, into 1 minus 0.0004279
to the power 3.
square. There are 2 transmission lines. So if you square this, you should get this. Compute.
So 0.3991448.
You have got it. Okay. And those next two, again simply it will be changed to 1, 1, 2 minus 1. Then the last one will be 2, 2, 2 minus 2. Okay. So accordingly. So in the exam, if similar question comes, then this part will be given as 4 marks, this will be 2 marks. So that is the whole generation model for this composite system. Now beyond this we have to compute the, as I said, LOLE, LOE. Okay, but that follows exactly the same thing as we saw in generation, so we won't repeat it here, but the solution is given here. This is the solution for the composite system. Okay, so you have to find out this P, the formula that I have written, generation, load, megawatt. Okay, so how this computed is given here using the formula, how these things are computed based on the departure of transmission and generation. Okay, so all this probability and frequency you can compute, but as you can see, it's very large a table to be asked in exam. So this may not be asked in the exam. If it comes, it will be a 60 mark question, not even 8 marks. Okay, so up to this it can be asked, but if you can develop this, you can always calculate this. It takes some time. Okay, then we will move to the PPT. So this problem is solved. So what are the observations? So these are the observations that we just discussed. You can go through it. Okay. Equation 5 includes possible transition between failure states and will therefore be given expected failure frequency. Okay. So we are actually creating the final result. The final result is a 21 state Markov model. The table that I have shown you, the last table. That is a 21 state Markov model. That is the final result. Okay. Evaluating the frequency of transition across a specified capacity boundary wall. The probability and frequency component for each state is weighed by the probability that the load will exceed the capability of the state to give the failure probability and frequency. Okay, that's it. So you see this observation, go through it. So this essentially completes the first part of composite generation and transmission system.